You ever have one of those days where it feels like the universe is just working against you? You know, like when you're trying to slide a heavy piece of furniture and it just won't budge? Or you're running and it feels like you're pushing against a wall of wind? Well, guess what? The universe is kind of working against you. But it's not a mystery, it's just physics. So today, we're going to pull back the curtain on 3 of these invisible forces you deal with every single day: friction, drag, and elasticity. Let's start with that first one, the one you feel every time you try to move something heavy.
Seriously, think about it. You've got a big heavy box you need to move across the floor. That first shove, man, it takes everything you've got. But then, once it finally starts sliding, it suddenly gets just a little bit easier to keep it going. What is going on there? Why is that? Well, the answer is all about our first invisible force.
So, first up on our list is that incredibly stubborn push. We're talking about friction, the force that, in a way, makes the world work, mostly by trying to stop everything from moving in the first place.
To put it simply, friction is the force that fights back anytime you try to slide one thing over another. It's happening on a microscopic level, you see. The surfaces of the box and the floor, they're not perfectly smooth. They're full of tiny hills and valleys that lock into each other. But here's the kicker. Not all friction is the same. This is where we meet the 2 faces of friction. First, you've got static friction. I want you to think of this as the grip. It's what holds an object in place, and it's the force you have to overcome just to get something to start moving. But once you do, once it's sliding, a new force takes over: kinetic friction. This is the slide, and it's the resistance you feel while the object is already in motion.
And here, right here, is the scientific reason that answers our big question. It all comes down to a little something called the coefficient of friction. It's just a number that tells us how sticky 2 surfaces are together. And the key is, the number for static friction, the grip, is almost always bigger than the one for kinetic friction, the slide. So in plain English, the grip is just stronger than the slide. That's it. That's the reason why that first push is always the hardest.
Okay, so you did it, you conquered friction, the box is moved. But now you look at the clock and you're running late. As you dash out the door, you're not fighting the floor anymore. Nope, now you're fighting the air itself. That invisible wall that seems to push back against you. That is our next force: drag.
Come on, you've totally seen this, right? In the Olympics or the Tour de France, you see these athletes in really high-speed sports, and they make themselves as tiny as possible. This is not just about looking sleek and cool. It's a very deliberate, very calculated move to fight against our next invisible force.
Now this is going to sound a little weird, but the air all around us, it's a fluid. And just like when you're moving through water at the pool, moving through the air creates resistance. That resistance is called drag force, and it is constantly trying to slow you down.
So, what decides how much drag you feel? Well, it boils down to 3 main things. First, the density of the fluid. Thicker air means more drag. Second, your speed. And third, your cross-sectional area. That last one is just a fancy way of saying how big of a target you are for the wind. So by crouching down, those athletes are literally making themselves smaller targets for the air to hit. That directly cuts down on the drag that's trying to hold them back.
But here's the part that's absolutely mind-blowing, especially when you're in a hurry. Drag doesn't just go up a little bit with speed, it goes up with the square of your speed. What does that mean? It means if you double your speed, say from a light jog to a full-on sprint, you are not fighting twice the air resistance. No, you are fighting 4 times the resistance. This is huge. It's why you really feel that wall of air when you're biking fast or driving on the highway.
All right, so far we've looked at forces that resist us, that try to slow us down. But what about forces that can store energy and then give it right back? For that, we turn to the incredible property of elasticity, the power behind everything from a simple rubber band to a massive skyscraper that's designed to sway in the wind.
The whole concept is governed by a beautifully simple idea called Hooke's law. All it really says is that the more you stretch or squeeze something elastic, the harder it tries to snap back to its original shape. That stiffness is measured by something called a spring constant. So a really stiff car suspension has a super high spring constant, while a flimsy little rubber band has a really, really low one.
Now, to get a bit deeper, physicists talk about 2 key ideas here. You have stress, which is basically the force you're putting on an object, like when you're pulling on a rope, and then you have strain, which is the result of that force. It's how much that rope actually stretches or deforms because you're pulling on it.
And this brings us to the different ways objects can be elastic. When you pull on something, you're testing what's called its Young's modulus. Think about stretching a guitar string to get the right note. When you twist something, like you're wringing out a wet tower, that's called shear. And when you squeeze an object from all sides, imagine the crazy pressure on a ball deep in the ocean, you're dealing with its bulk modulus. Each one of these just describes a material's unique power to resist being changed and then snap right back.
So there you have it. Friction, drag, and elasticity. I know, they might sound like boring words from a textbook, but as we've just seen, they're basically your silent partners in almost everything you do all day long.
Let's just quickly recap our day, shall we? That first, really hard push to get the box moving, that was your epic battle against static friction. That wall of wind you felt when you were running for the bus, that was you fighting air drag, a force that gets way, way stronger the faster you go. And that simple little act of snapping a rubber band, you were literally watching the stored and released energy of elasticity in action.
These forces are absolutely everywhere, quietly shaping every single thing you do. So the next time you slip on an icy sidewalk, or feel the wind on your face on a bike ride, or bounce a ball, you'll know the names of the invisible rules that are at play. But that leads to a much bigger question, doesn't it? What else are you missing? What other invisible forces are orchestrating your world right now? If you just look around, you'll see the answers are everywhere.